Hi folks, we're going to take a look at number 13 from page 481. So they want us to determine all the different equations of the plane containing these two lines. All right, so normally when we have a plane which contains two lines, we can just use the direction vectors for the two lines as my direction vectors for the planes. But here I notice that the direction vector for line 2 is exactly 2 times the direction vector for line 1. Okay, which means I cannot use these to determine the equation of the plane, but I certainly can use one of them, and I'll use the simplified version of them. Okay, so if we label our direction vectors for the plane as A and B, I'll take 1, -3, -5 as one of the direction vectors. All right, so in order to find the other direction vector, so clearly these lines are on the plane, but they're parallel. So I'm going to take a point on each line, which I've given, and I'm going to use that as my second direction vector. All right, so here for direction vector B, I will take the vector joining those 2 points. So what do we have? We have 7 minus 3 is 4. Then we've got -1 minus -4. So -1 plus 4 is 3. And then we've got 0 minus 1, -1. All right, so this is going to be our second direction vector. So once we have our two direction vectors, we can start by writing the first two equations, which are going to be the vector equation. All right, so I can write, pick either point. So I'll pick 3, -4, 1, since they're both on the plane. So plus s times the first direction vector, 1, -3, -5, and then plus t times the second direction vector, the one we just found, which is 4, 3, -1. And of course, s and t, we have to say, can be any real numbers. All right, so from there, we can rewrite this in parametric form. So x is going to be equal to 3 plus s plus 14. All right, then we go to the y value is going to be -4, okay, minus 3s, and then here plus 3t. And lastly, z is going to be equal to 1 minus 5s, and then here minus t. Okay, where again s and t can be any real number. All right, so to find the Cartesian equation, now we're going to have to find a normal vector. And of course, what I'm going to do is I'm going to take the cross product of the two direction vectors to give me my normal vector to the plane. Okay, so find my normal vector. So I'll place them one over the other to use my little trick. 1, -3, -5, and 4, 3, -1. 1 and 4. So let's see what this gives us. So this gives us 3 plus 15 is going to be 18. Here we've got -20 plus 1 is -19. All right, and lastly, what do we have? We have 3 plus 12 is 15. All right, so now that I have my normal vector, now here I would see if I can actually reduce it, but I can't because of the -19. So I'm going to take this with one of the 2 points. I'll take the 3, -4, 1, since I know that that's on the plane, and find my d value. So I have 18 times, so what's my point there? 18 times 3 minus 19 times -4 plus 15 times 1 plus d is equal to 0. And I think I'm just going to use a calculator here to do this. So let's see what we've got. We've got 18 times 3. That's going to be plus 19 times 4, and then plus 15. Okay, so we have 145. Bring that to the other side, so d is equal to -145. All right, and so now we can write the equation. So we've got 18x minus 19y plus 15z minus 145 is equal to 0. Okay, so just to recap here, while I did have two lines on this plane, they happened to be parallel, so I couldn't use the two direction vectors. I could only use one of them. In order to find a second direction vector, I just found the vector joining the 2 points that I had on the plane. give a quick check. These are obviously not parallel, so they can be used to find the vector and parametric equations. And then we take the cross product to find a normal vector and eventually solve for D. Okay, that's it for this one.